Buonasera, benvenuti a questo nuovo appuntamento con i Meetup per i Tech Online Edition di Codemotion. Questa sera siamo con la community di Deep Learning Italia. Io mi chiamo Paolo, farò una breve presentazione su cosa facciamo a Codemotion, cosa sono gli Apritech e poi lascerò la parola agli organizzatori del Meetup. Cosa sono gli Apritech? Gli Apritech sono un circuito di eventi ideato da Codemotion, che viene organizzato e creato in collaborazione con le community come questa. Qui a video potete vedere i nostri canali, i nostri riferimenti. Abbiamo il canale Telegram e il nostro Dev Calendar, un calendario con tutti gli eventi presenti, passati e futuri. Dico anche passati perché c'è la possibilità di vedere anche i video, le registrazioni dei vecchi eventi, quindi vi consiglio di dare un'occhiata al nostro Dev Calendar e di registrarvi. E abbiamo anche il nostro gruppo Facebook Codemotion Tech Community, che vi invito ovviamente a registrarvi perché potete restare aggiornati su tutto quello che facciamo in Codemotion e appunto tutti gli eventi che organizziamo. Andiamo avanti. Ok, qual è la missione di Codemotion? La missione di Codemotion è appunto quella di dare un aiuto, una crescita professionale agli sviluppatori. Come lo facciamo? Tramite i nostri eventi, i nostri training program, i nostri online hackathons, i coding challenge, il nostro dev magazine, appunto dove trovate tantissimi articoli tecnici, e una sezione dedicata completamente alle community. A proposito di questo, ovviamente vi ricordo il sito che è codemotion.com. Per quanto riguarda le community, vi segnalo i prossimi eventi in calendario. Andando sul sito community.codemotion.com potete vedere tutti gli eventi e seguire questa o altre community. A proposito di community, se avete gli skill necessari o vi sentite in grado di creare una community, Codemotion vi dà la possibilità di creare una community e quindi di gestire una community e restare in contatto con noi, che ovviamente vi aiuteremo per creare gli eventi e tutto quello che ruota attorno alle community. Quindi prendete coraggio e create la vostra community. Una novità che a breve verrà iniziata da Codemotion è il DevCast, ovvero ci sarà un appuntamento settimanale. Il primo sarà il 25 di febbraio alle ore 5, quindi segnatevelo nel calendario, dove appunto ci sarà uno spazio dedicato alle ultime news sul mondo tech. Verranno intervistati, avremo grandi speaker e ci sarà anche il Codemotion News, cioè un nuovo TG dedicato appunto al mondo tech. Quindi non perdetevelo. Vi ricordo che il 23, il 24 e il 25 di marzo ci sarà la conferenza online di Codemotion, ovviamente l'edizione italiana. E ovviamente questa qua, come già molti di voi sanno, è la conferenza che è fatta da sviluppatori e per sviluppatori. Quindi non mi dilungherò tanto, ma vi dirò solamente che rispetto all'edizione precedente, questa volta le tematiche saranno 5, avremo 5 tematiche divise in 3 giorni. E voi, grazie avete la possibilità questa sera, partecipando a questo webinar, di collegarvi a questo link, qui che vedete qui in alto, e avete la possibilità, grazie alla community di Learning Italia, di ricevere un biglietto premium che vi darà diritto a dei benefici che potete vedere qui online, qui sulla slide. Detto questo, io ho finito la mia presentazione. Vi ricordo solamente che se volete fare delle domande, potete cliccare sul pulsante alza mano. Io vi attiverò il microfono e potrete fare direttamente la domanda. C'è la possibilità di fare anche le domande in chat, poi ovviamente vi esorto a alzare la mano e attivare il microfono. Detto questo, io lascio la parola ad Andrea.
Okay, so let's switch to English. So good evening and welcome everyone to today's meetup. I'm Andrea Gatto. I'm going to be with you for this and for the next talk. So just a quick introduction about Deep Learning Italia for those of you who don't know it. So Deep Learning Italia is a community focused on deep learning. Surprise. So if you're interested in deep learning, machine learning, data science, and so on, I invite you to subscribe to the Meetup page in order to stay up to date with upcoming talks, events, and so on. Speaking of future talks, since you're here attending this very interesting NLP, in particular natural language generation talk, I also invite you to join us on March the 16th for the next talk that is going to be also about natural language generation. So that being said, I'm very happy to introduce today's speaker, Patrick von Platen. So Patrick is a research engineer at Hugging Face. I suppose that many of you have already heard about them. They are the company behind some very famous and amazing libraries such as Transformers. So Patrick is a core maintainer of the Transformers library, and his work focuses on encoder-decoder models, sequence-to-sequence task, long-range sequence modeling, natural language generation, so pretty interesting stuff. And before joining Hugging Face, Patrick was also doing some research in the field of speech recognition at Uber AI, at Cambridge University, and also at Aachen University. So I think that's it for the introduction. As already discussed, concerning the questions, there will be a Q&A session after the talk. So feel free to raise your hand if you wish to speak, or you can write down your questions in the chat, and Patrick will answer them during the Q&A session. So I think that's it. Thanks a lot, Patrick, for being with us, and thanks everybody for having joined us. So yeah, Patrick, the screen is yours. Patrick?
Awesome.
Yeah, cool.
All right. I hear me? All right, okay.
Yes,
I think, yeah, everybody can see my screen now, so let's just share it. Great, okay. Yeah, so welcome everybody. My name is Patrick. I'm a research engineer at Hugging Face, and I'm very glad that I can present to you today some concepts, trends, limitations about transformer sequence-to-sequence models. So in the beginning, I just wanted to talk a bit about Hugging Face. So at Hugging Face, we raised 50 million last year in December. Actually, well, now it's like two years ago, to build like the definite open source library, which is Transformers, which some of you guys may know. And Transformers has grown very popular. So we have over 1,000 research paper mentions now. We use in production by over 1,000 companies, and we have over 5,000 pre-trained models in the model hub, which you can see at the bottom here. And 40,000 daily pip installs, and now also over 40,000 stars. Yeah, the philosophy of Hugging Face is really to kind of make research accessible for everybody. So we kind of try to balance our two extremes. One is to have our code as adaptable and tweakable as possible for everybody, but at the same time, we want our code to be used in production. So we can try to balance out between very flexible and readable code and very easy to use code. We participate in a lot of workshops, events, NLP, and yeah, well, like our main philosophy is really to make people stand on the shoulders of giants. It means that we really try to leverage knowledge from the big tech companies, from Google, Facebook, and make it accessible for everybody. Cool. That being said, we can jump right into the talk now. So yeah, today I want to talk a bit about well, a short intro, kind of like what happened in the last 2 years, how Transformers took over NLP. Then I want to talk about the architectures that there are currently in NLP. Then we're going to talk about the pre-training objectives, so the self-supervised training, and then about some current trends, and last about some limitations. All right, cool. So let's go to yes, let's go to 2017. In 2017, the Transformer paper came out and kind of showed a large improvement over the state of the art at that time, which was the sequence-to-sequence model. And so first of all, the sequence-to-sequence model was the first end-to-end model that successfully kind of tackled sequence-to-sequence problems. And it became that prominent that actually Google used it in their Google Translate service. So at some point, Google just scraped their whole rule-written code of translation and replaced it by a single neural network, a sequence-to-sequence RNN. Yeah, and RNNs work as follows. There's an example now for translation, which is sequence-to-sequence task. So you can put in a word embedding vector in the beginning, the I. It's going to be encoded by the RNN, and then you kind of cache it in the memory. And then you put in your second vector, want, and then process together with the memory to your new memory, and then so on. You put in your next word embedding vector, until you kind of encode the whole sequence, which is in this case, I want to buy a car. So you do it one by one sequentially until you get your hidden state, which is just a representation of the whole input. This, like, normally it's more or less of the same size in the input vector. And what you do then is you autoregressively generate the output. So you kind of start with a dummy token with the beginning of the sentence token normally, and then you generate one by one the next words. So we go from ich then to will ein Auto kaufen. So it's a German, there's an English to German translation here, and you kind of see it both sequentially processes the input, stores it in a hidden vector space, and then also sequentially autoregressively generates the output, where you put a dummy token in, sample from your logits vector, and so forth until you're done and you reach the end of sentence token, which is a hint to the model. Right now the sentence is finished, and you have your translation. So why did it work so well? The RNN sequence-to-sequence worked so well because it was the first model that could kind of model input dependent output length. So what that means is in a sequence-to-sequence task, the output length actually depends on the content of the input, not just input shape. So normal feed-forward layers and convolutional networks, they can't really handle that, which is why you can never really use a single kind of like feed-forward network or a convolutional network for sequence-to-sequence tasks. The problem though is that it had some pitfalls, the RNN structure, and the big one being that it's very difficult to parallelize. So as you've seen in the input here, you have to process every token one by one, even though you know what your input is. You know from the very beginning that you're going to process the whole sentence and not just one after the other. So that makes it kind of slow to train and also later to use an inference. The second big problem of RNNs is that you cannot really model long-term dependencies very effectively. That means, for example, if you want to model the relationship between, let's say, we're going to use the word by because it's a bit later in the German translation, it's the very end. You see there are a lot of computations that you have to go through until you can kind of put those two word embeddings into relation with each other. And this can be a problem when you train it because the gradient has to flow through all those computations, and this often leads to catastrophic forgetting, which is also why LSTMs were invented and multiple tricks were invented for RNN. And the last pitfall is that you can encode your whole information in one single one single hidden vector. So even if the sequence has a length of, let's say, 20, you're still gonna try to compress all this information into one single vector, which is not that good by design because you can lose information. It makes it very hard for the model to kind of remember the whole input, especially if it's very long. Cool. All right. So now let's see what worked better. And there was the transformer network in 2017 with the attentions-only need paper. Here, what the transformer network can do very well is it can process the whole input at once. It can parallelize over the input, which is very nice. And then what it does similar to the RNN, it's going to generate the output autoregressively again. So it's more or less the same thing that happens. You put in your beginning of sentence token, you generate a logit vector, which is a vector over the whole vocabulary. You sample the most likely, and so forth until you autoregressively. Oops, that was a bit too fast. Autoregressively sample the whole sentence. So the big advantage is highly parallelizable. So you can put your input in at once, and in inference, you still have to sequentially generate the output. But doing training, you can input your whole source, kind of like language sentence, and at the same time also your target language sentence in one kind of like forward pass. it can generate you the loss for all those output tokens. So it's much easier to train, or much faster to train. Yeah, and the last two big advantages is, first of all, you don't lose information, because you have a hidden output sequence here instead of a hidden output vector, which makes it much easier for the model to remember the whole input. And second of all, it's very effective at maintaining long-term dependencies, which means if I use the same example as before, now kind of like the relation between buy and kaufen, the translation of the word, is 1 essentially, because every layer has direct access to all encoded vectors, which means that it's literally just like a one operation relationship, which makes it very easy to train and allows the model to better remember long-term dependencies. Cool. All right, then let's jump to 2018. In 2018, BIRD revolutionized the field by transfer learning, by self-supervised learning. And the big change was that previously in attention all you need, the model was just trained on a normal downstream task. So you give it a translation task, I think it was German to English mainly, and you train the model from scratch. The difference was now that BIRD and GPT, that those models, they were just unsupervised trained on any tokens of the internet, so you didn't need any labels. And BIRD really showed that this can drastically improve the performance on downstream tasks afterwards. And I kind of put some shortcuts as some snippets, some shortcuts and snippets from the internet. And you can see that BIRD is now used actually in Google search, which is pretty impressive. So research finished in late 2018, and now we use this research in production in one of the biggest searches in the world. So that's pretty cool. OpenAI, with GPT-3, they released an inference API, which also kind of goes directly from research to production. And so that's pretty impressive. And now I wanna recap real quick what transfer learning is. So in transfer learning, the big change is that you have a base model which you randomly initialize with some weights, as you usually do when you train a network. And then what you do is, first of all, you use a very large corpus, which normally doesn't even have labels, so you can just scrape the web. You can just use the whole of Wikipedia or other open source texts. Then you need a lot of money for the compute. And then lastly, you also have to train for a very long time normally. Okay. Does that still work? What happened now? Okay, that's weird. Sorry, I hope everybody can still see the screen. All right, let's try that again. Okay. Don't know what happened there. All right, so yeah, transfer learning is a very large corpus, lots of money in compute, and days of training. And then what you gain afterwards is you get your pre-trained model, which is then BIRD or GPT or Elmo. And this model was just trained on unsupervised data. So that means you can use it pretty much in every downstream task afterwards. And BIRD really showed that this helps a lot. So you can use this pre-trained model on a downstream task which has very few labeled data and performs very well. So the next thing is then you pre-trained your model, you can reuse that. So now what you do is you just fine-tune the model. So again, we use our pre-trained BIRD. And now what you do is a small data set, like the glue tasks. Training can usually be done on a single GPU. Some of the glue tasks can literally just train in a Google Colab, and you get state-of-the-art results, which is pretty cool. And it's also it's very easy to reproduce, which is also one of the big reasons why I guess Transformers Library was so successful, because people can just reuse checkpoints and kind of see whether they can reproduce the results of the paper by fine-tuning it on a single GPU for some hours. All right, cool. That should have been a small recap. So now we're going to jump into some more details. This slide shows you the different transformer architectures that there are right now. I guess there's some other ones, but those, I guess, the other general ones which I want to present here. And first we have the Autoencoding Models, which is BIRD. Then we have the Autoregressive Models, which is everything which is GPT. So Autoregressive autoregressively generating language. Then you have the prefix models, which are kind of like a mixture between the two. In the beginning, you have bidirectional self-attention. Then afterwards, you have unidirectional self-attention. So mixture kind of BERT and in GPT. XLNet is, for example, one of those models. And then lastly, the focus of my talk is going to be the sequence-to-sequence models, where you have an encoder and a decoder model. So that's quite different actually from the other models. I'm going to talk about more on this later. So yeah, let's talk first about BERT or BERT-like models. So we call those models autoencoding models, and they're usually used to do sequence classification or token classification, and they're especially effective at sequence classification. So you want to classify the whole sequence into multiple labels. For example, natural language inference is one where they want to know whether two sentences follow each other, or whether they contradict each other, whether they're neutral to each other, or whether they agree on each other. So it's everything which is related to natural language understanding. What you do here is you kind of put in your inputs. Then you have bidirectional self-attention, what you can see here. So every token attends to every token of the input. So even the first token is going to attend to the last token. It's very important if you want to get a good representation of each word, which depends on all other words. And then you just kind of transform it forward until your last transformer layer. You get your hidden sequence. And then what you do is you just put one linear layer on top normally, and you classify it to how many classes you want. And that's classical BERT setup. And most models actually we have on our model hub are like that. So it's BERT, DistilBERT, ALBERT, all those BERT-like models. They have this architecture. And those models are pretty efficient because you normally just do one forward pass. There's no autoregressively generating the output, but it's just one forward pass, and you have your classification. All right, then next one is GPT. So that's like the classical GPT 1, 2, and 3. What they model is they model the next token given the previous tokens. So what that means is you give it a token y0, you pass it forward, and the model is going to predict or give you a probability distribution of the next possible token, and then so forth. So when you then put in 3 tokens, then it's going to give you the probability distribution for the 4th token. You sample from it, put it in, and so forth. The important thing is here that you have unidirectional attention, which means that the first token is not allowed to attend to the 2nd token or 3rd token. Otherwise, the model could just cheat. The model would always just be like, all right, I know what I want to input here. I'm just going to predict that here. So that wouldn't work. You couldn't model anything. So that's why you need to kind of mask those attention connections. It's very important. And yeah, those models, well, actually you can use GPT for pretty much everything. I mean, everybody knows that GPT-3 works on pretty much every task, but they're mostly used, or they were mostly used in the early days just for open text generation. So if you just put in a prompt, for example, y0 to y3, and it's going to generate the rest for you. Cool. Next one is a prefix language model, which is a bit special, so I don't want to spend too much time on that. Yeah, the prominent models, I guess, are XLNet and UniLM, so they're kind of like the I think unified language model. What's it called, the paper? And what that does, the model, it kind of says, right, I want the best of both worlds. I want both the bidirectional self-attention and the unidirectional self-attention. So what you normally do is when you do conditional language generation, which is sequence to sequence essentially, you say, all right, your input is going to be x1 and x2, for example, is going to get bidirectional attention. So x1 can attend to x2. But then you're going to autoregressively generate the output. So what you learn then in your target is you're going to learn like a unidirectional attention pattern. Yeah, and this model is a bit special, but it's shown to work very well for sequence-to-sequence tasks. All right, but it also, yeah, because of the structure, it also works very well for just natural language understanding, so BERT-like. This just means then you just only use X's and don't use the Y's. The important thing again here is that the weights are shared. So your attention projection weights for the query key and value, they're shared. Yeah, which makes it possible to use this model in both settings. Cool. All right, next model is our important model, which is the encoder-decoder. And this one is a bit special now. So what you do here is you encode your input sequence, as I explained earlier already, actually. And then you have your hidden state sequence. You condition then your decoder on that sequence, and then you autoregressively generate that again. So it's a classical sequence-to-sequence architecture. It was used for RNN previously, and it's just a translation for transformer networks. And yeah, the prominent models are Bart and T5. Those were the first two models that really, and I guess like the original transformer as well, but Bart and T5 were the first two models that really used transfer learning on the transformer and decoder architecture. All right, now the question is, yeah, what should you use for sequence-to-sequence tasks? So you can really use BIRD, because BIRD just classifies your sequence and it doesn't have any unidirectional attention, so it can really generate the next word. You can use GPT-like models, so just the language model, the autoregressive language model. But yeah, it's been kind of shown that it's unnecessarily limited in the sense that even your input, what you want to condition your model on, let's say like the English sentence, if you want to translate it to German, the English sentence can only attend always to the next token, even though you know the whole input sequence. So the last word in your input sequence should also be able to attend to the first token, which it cannot do in GPT-like models, which is an unnecessary restriction actually. Yeah, the prefix LM has been shown to work very well, but is also inherently more strict than sequence-to-sequence architecture, in the sense that you kind of force the output to be of the same length than the input. I'm going to talk about this later a bit more in detail, but this kind of means that it's very hard kind of to train the model on like masks that you want to generate for a whole sentence. So what you have to do here is actually you have to kind of accept that when you pre-train the model, that a mask token that you put in has to be generated, which means that like if you want to force the model to generate the whole sentence, you have to put one mask for every token in the sentence. You cannot kind of force the model to learn the length of the mask it has to generate itself. Yeah, and lastly, well, the sequence-to-sequence models, I mean, it has been shown that they work the best, but a lot of people always think that they have more, well, I mean, they have more parameters. They have an encoder and a decoder. So it's normally like, they quite often have twice as many parameters as just normal autoregressive language models or prefix language models. But the thing is that the encoder of the sequence-to-sequence model is only run once. And this normally means that the model is more or less as effective in inference or doing training as the other models, because it's only the decoder that generates autoregressively, and that again is has the same size as the other models. So yeah, I took this table here from the T5 paper, which is a great paper by Colin Raffel, and he kind of compared all those different architectures, and you can see that encoder decoder outperforms all the other models pretty much on all tasks, especially the normal kind of like language model is much worse, as you can see here. So there's a big gap. Yeah, prefix M works pretty well, but it still doesn't work as well as the encoder decoder. All right, cool. Now we've covered that, so we should know about the architectures. Now let's talk about pre-training. So I think everybody knows the BIRD-like pre-training. So what made BIRD so successful was the idea of that you can just input a sentence, you mask one token, and then you force the model to generate this token. And what BIRD did is it said, right, it's randomly mask 15% of the tokens, and then we're going to force the model to predict those tokens. And they did this on a lot of unsupervised data, so no labels, and this worked very well to get a good understanding of general language. You get a good kind of like language representation. Then the other like known pre-training paradigm is the language model style, where you just say, all right, the model should just learn to predict the next word. So what happens here is you give it a prompt, and then at the moment you put in like your $, for example, the model is forced to learn that the next token is A. And you say, all right, now I know that it's A, then the model is forced to learn that it's robot, and so on. So it's always going to learn the next word. And that's just the classical GPT-2 style. And you also don't need labels for that. You can just take any sentence from Wikipedia on the internet and train your model on that. Now, one small kind of extension to that idea was SpanBird. So in SpanBird, what you do is the author kind of had the idea of, all right, let's say I kind of like my model should be able to generate a whole sentence and not just a token, because it's much easier. I mean, if you just mask one token here, it's kind of much easier to predict this one token. So you can kind of like intuitively think that, right, the model after training is not as powerful, because all it can do is it can just kind of guess what one token is given the bidirectional context. What is better is actually if doing pre-training, you force the model to kind of guess the whole sequence. So what you do here is you just mask multiple tokens in a row, so a span of masks, and then you force the model to predict those. So this has been shown to give better results later on downstream tasks, which kind of means that this is a better pre-training objective or inductive bias kind of for the model. Now the big problem is what I kind of already touched on earlier, is that the model still, like, you have to show the model the output length. So that means if you put in 4 mask tokens, the model knows it's going to generate exactly 4 tokens. And that's a big hint you give to the model. And so the model never learns itself how many tokens to generate if you have an encoder-only architecture. And now there was a big change for sequence-to-sequence models, because when you pre-train those, what you can do is you just say, all right, like, I'm not going to even tell my model anymore how many tokens it should generate. I'm just going to tell it you should generate something in there. So that means for sequence-to-sequence, what is shown here in this diagram, which is also from the T5 paper, is that you mask a span of tokens. So again, for inviting, but you can replace it by a single mask token. And well, the same here, just for 1 token, but it doesn't really matter. You can also just mask a whole sentence by just 1 token, because it's the encoder input. So then you get your hidden states, and then the decoder has to figure out itself how many tokens to generate. So what you do here is in the target is just is for inviting for this token, for the mask token, and last for the other one. But you can see that 1 mask token is kind of like, it has a target of 2 tokens in this case. And this has been shown to give much better pre-training, because the model now not only learns what tokens it should generate, but also how many tokens, which is kind of given by default to BERT. Yeah, and we work with some research groups that even use just the sequence-to-sequence kind of pre-training, and then throw away the decoder for inference and just use the encoder for inference, which just means that, right, they want to have this better pre-training kind of paradigm for their models, even though they don't even need an encoder-decoder model, they just need an encoder model. Yeah, and the second diagram I want to show here is that's from the Bart paper, that you can pretty much, in encoder-decoder setups, you can do a lot of different things for pre-training, because all of this is input in the encoder, and then since the decoder is going to autoregressively generate whatever you want, you can do a lot of different things. So you can just say, all right, like, I'm going to delete some tokens from the inputs, and then I'm going to force the decoder to kind of know that I deleted a token, and that the decoder then has to generate it, which is shown here. Or you can do text infilling, which is very similar to this one, rotation, whatever. But in short, it's just kind of like the crux is that encoder-decoder models, they have much more kind of liberty for different pre-training objectives. So this means you can kind of like teach the model better what it should learn, and you can give it fewer cues so it learns by itself. Yeah, and this has been shown, especially in the T5 paper, to work extremely well, also for just encoder-only downstream tasks like Glue. Cool. All right, then let's go to some trends. So yeah, I guess the trend that everybody's been noticing is the models grow in size. So and that's pretty crazy actually, because I guess back in the days in 2018, people thought that 90 million parameters is a big model, and now that's nothing. Now you go up to, well, like over 100 billion in the case of GPT-3, or I think recently the Google had over 1 trillion, I think. So models scale like crazy, and so far it's been shown that bigger models get bigger results, get better results, but it's often not feasible to use these models in practice. I mean, GPT-3 can really be used by small companies that don't have a huge GPU or TPU cluster in the end. Yeah, that's also why we with Hugging Face we work a lot on distillation and just making very powerful models kind of smaller and accessible for everybody. So DistillBird, for example, reaches a very high accuracy on Glue while being a tiny model in comparison to all those big models, which means that DistillBird can be run much faster, pretty much by everybody. Yeah, so this is a very general trend. This is not only for sequence-to-sequence models, but it's a very general trend that kind of shows up for all models and for all NLP tasks. All right, then yeah, the second kind of slide for the current trends. This is specific to encoder-decoder models. So one very cool paper was also by Google, which is called Leveraging Pretrained Checkpoints for Sequence-to-Sequence tasks. Oh, sorry, this is actually, no, that's something else, my bad. So yeah, no, this is sharing the encoder and decoder weights. Yeah, so it's also very interesting. So what you do here is you just say, all right, the encoder and the decoder, they have the same weights. And this might be a bit counterintuitive because you often think, all right, the encoder is a very different task from the decoder. So for example, when you do translation, when you do English to German translation, the encoder is going to encode a German sentence, and the decoder is going to generate an English sentence. So by default, you would think, right, these models, like these parts of the models are different, so they need different weights. But it's been shown that this actually works quite well. You just use the same weights, so you save memory, you save some inference time, and you get good results. Yeah, the crux is though, for specific tasks, like especially for summarization, for things like on the CNN daily data set where you do abstractive summarization. So you have a long article and you want to generate a summary where you can like pick the important sentences out of the article. This works extremely well, actually, sharing the encoder and decoder weights. And yeah, in the paper I talked about earlier, that leveraging checkpoints for pre-trained checkpoints for encoder decoder models, they show this actually works better sometimes when you have limited data than not sharing the weights. For tasks like translation, it works well as well, but it's normally not better. It's a bit worse than not sharing. If the distribution of your input and the output is not very similar, which is not the case in translation because you have different languages, then normally you don't want to share the weights. If they're very similar, say summarization, because the input are sentences and the output are sentences, and they're normally of the same length and same kind of style, then this works pretty well. So yeah, and you can see like you save a lot of parameters when you share. So here BIRD share has more or less half the parameters of BIRD to BIRD, what they show in their paper here, and gives even better results in some tasks if you have limited data. So there can be a very good approach as well when you're limited by your RAM. You can just share the weights, and that works only very well. The next kind of trend was, or like I want to talk about is Pegasus. So there was a paper that I think not too long ago was published, and the idea is here that you do task-specific unsupervised pre-training. So they get again like meaning again because like you have that freedom in encoder decoder pre-training. You can just kind of do whatever and it works, and you can adapt your pre-training objective to your actual tasks. So that in Pegasus I said, all right, we want to have a summarization model, so we're going to directly pre-train the model on summarization. And what they did here is they said, all right, we're going to do two different objectives. One is just like a BIRD type objective of your encoder. So you just mask, and those are the mask2 tokens. You mask single words and force the model to predict them, classic BIRD. But the other thing is very interesting actually. So what you do here is you say, all right, the model kind of has to learn from different sentences what is the most important sentence, and also maybe like what is like the summary of those sentences. So what they did is they just mask a whole sentence with a mask1 token, and then force the decoder to learn exactly that sentence that they mask. And you know, like in training, I mean, you give it this input, so the decoder input, because that's what it should learn autoregressively, and you give it this input. But during inference, I mean, you only give it the encoder input and it has to generate that. So it makes a lot of sense, this pre-training objective for summarization. And they even went so far to kind of like find automatically the most important sentences in the text corpus. And what they did is they just kind of chunked an article into all those sentences. Then they said, all right, let's compare the sentences with each other, with each other sentence, and the sentence with the most overlap of all other sentences is most likely an important sentence. So they mask this sentence and let it can generate by the model, or like let the model learn to generate this sentence. And this is all done without labels. So this is all unsupervised fashion, and it's been shown to work like extremely well actually. So Pegasus, I think is still the state of the art on quite a lot of summarization data sets like CNN Daily Mail and the BBC Extreme Sum dataset. All right, okay, next trend. Yeah, next trend I want to talk about is the long-range sequence modeling. So there have been a lot of papers on long-range sequence modeling, because everybody knows that the attention has a kind of like a sequence length squared memory complexity, which blows up very quickly. If your input is longer than, I don't know, let's say 2000, then normally your memory can't handle it, because you have a 4000 by 4000 attention matrix, and it doesn't work. So BIRD, for example, is by default just limited to 1212, and most models are limited to 1024. But you need long-range sequence modeling. For example, if you think about, I mean, if you want to summarize a whole news article, this is normally longer than 1000 tokens. And in this case, you need some mechanism that kind of allows you to memory efficiently attend to all the tokens. And there's a lot of work, especially on Encoder-Only and Autoregressive models. So it kind of started with XLNet, Transfer XL, all those kind of like memory type models. Then they came Reformer. And now recently you also see papers kind of tackling long range for sec-to-sec. One is the BigBird paper, which I show here, and the other one is Longformer. They're very similar in the sense that they both use sparse attention. So what you say is, all right, you're just going to attend locally. In addition to attending locally, you're also going to have some tokens which attend to the whole input. So this way, you don't have your n-squared attention. You just have like your local window squared times the number of tokens. And then you have some tokens which attend everything, but this more or less scales actually linearly. And the results have been also very good. So I think both the BigBird and Longformer encoder decoder, which we call LED in transformers, they give state of the art on long range summarization, like the ArcSive dataset, or also I think PubMed is the other one. Another task is also a question answering. If you have a huge context and you want to answer a question, you also need long range sequence modeling, and sequence to sequence works very well normally for those kind of things. Cool. The last thing is what I kind of already talked about in the very beginning is warm starting sequence to sequence models from pre-trained checkpoints. So the idea is your sequence to sequence model is an encoder decoder model. So we have essentially two BIRD-like models. So why not just use two pre-trained BIRD checkpoints and then directly fine-tune the model on a downstream task? And this was the idea of the paper that I link here, which is called leveraging pre-trained checkpoints for sequence generation tasks. And they show very good results. So it's very nice, because you don't have to do any costly pre-training. You can just kind of use two pre-trained BIRDs, and then you just fine-tune on a downstream task. So for example, summarization. And we like that a lot at Hugging Face, because we're all about kind of saving pre-training time and being very efficient. So we built this framework, which is called the Encoder-Decoder model framework, where you can essentially load whatever encoder-only checkpoints you want. This for the encoder, this for the decoder. So literally like in 2 lines of code. You tokenize your article if you want to do summarization, tokenize your summary, and you can directly learn the model on the downstream task, which is summarization in this case. So it opens the possibility for a lot of different combinations. So if you have a very good, let's say, decoder, and then maybe like a long-range encoder, you can put them in here. So for example, you put Longformer in here, and then you can put in like a ProfitNet or Bart head here, decoder head here, and then you have your sequence-to-sequence model with the pre-trained checkpoints, and you normally only need to fine-tune that on your downstream task, and it works like surprisingly well. So on the paper, the models, they give competitive results to state of the art, which is great. All right, last topic is going to be some limitations and shortcomings. So this is also again like something which is not only limited to sequence, but it's limited, but it accounts for all encoder, for all NLP models essentially. So it's the classical things. Kind of one thing is problem that like the data we give to models normally doesn't include the obvious statements. So what that means is that there's a lot of knowledge that we just have. We don't really state. I guess like the classical example is that you never write down that a sheep is white, because everybody knows that a sheep is white. You don't have to write it down. So there's no data that says that sheep are white. So there's much more data that says sheep are black, because it's a metaphor. So models then think that sheep are black just because we don't state the obvious. We don't state the things that everybody knows or should know. There's also, yeah, there's like common sense is written down, it's very similar. Yeah, some other problems is that NLP models usually only, well, I mean, there's a lot of research on that as well at the moment, but most NLP models still only use text as an input. But we humans, we use so much more, right? We use vision and we use sound as well to understand the world around us. So the models kind of miss out on a lot of things. Is again, for example, the sheep example. I mean, if we see a sheep and we know that it's white because we see it, but if you just give text, there's no way to learn it. So yeah, I mean, there's a lot of work going on at the moment also of combining, for example, especially image and text, which is then called multimodal kind of NLP models, and it's been shown to work very well, and it's a very interesting approach. And then a huge thing is also that is the continuous training problem and the catastrophic forgetting if you kind of retrain the model again. So, for example, GPT-3 doesn't know who the current president is of the United States because it wasn't trained on data that is that stated that Biden is the current president. So GPT-3 thinks that Trump is still the current president. And this is a big problem because it's not that easy to just say, all right, this is a pre-trained model. I'm just going to update it now with new data. Because what happens quite often then is then you forget everything you've learned so far. So this is a huge problem actually. And kind of also says that GPT-3 needs to be constantly updated in a very smart way. So because you don't want to always start from scratch, because it's like training GPT-3 costs, I don't know, like $10 million US. So you can't do this all the time. One very nice approach to tackle that is retrieval augmented models. So this paper is the RUG paper, which kind of use an external database in between. So what you do there is you kind of embed your question. For example, if you were to ask like who's the current president of the United States, you embed that question and you compare your embedding to an external database, which is not a model, which has no model parameters, but which is literally like a database. Then you compare your embedding to all embeddings in the database, and then you retrieve the best, or the most likely kind of like data in your database, and then you generate the output. And the cool thing is here that you can just change the database to an up-to-date database, and it works very well. So this is a very nice approach to kind of keep up to date with the current information. Yeah, cool. All right, then let's go a bit again to limitations and shortcomings for encoder-decoder models. So the biggest thing is that autoregressive generation is very expensive. So the thing is that transformers is much more efficient than an RNN, but on the other hand, the decoder of a transformer sequence-to-sequence model still has to autoregressively generate the output. So these designs showed you earlier, and this is pretty expensive. Because your transformer model can be very big, and you also normally use beam search, not just normal kind of arc-max search, which means that your decoder is pretty heavy and can take a lot of compute and memory. And that's also the reason, for example, Google Translate doesn't use transformer as a decoder. They use the transformer as an encoder. They still use an RNN as a decoder because it's just so much more efficient in inference, because RNNs are smaller. They're not sufficient to train. You can parallelize. But in inference, when you have a small RNN decoder, it's faster than a transformer decoder. So transformer is very, very efficient at training, and is very efficient at kind of processing the input directly once, but it's not very efficient at generating autoregressively. And that's a big problem. So super simple approaches are that you just say, all right, like my encoder can be very big, my decoder shouldn't be big. So what you do here is that you just, for example, say I'm just going to use one AttentionNet for my decoder, which makes it much, much faster, which is a very nice paper here by Noam from Google, or this paper here from Sam, who used to work at Hugging Face. He just shows that if you kind of compress your decoder much more, so you just reduce the number of layers by a factor of 2 and the number of attention heads, you can still kind of get competitive performance while being much, much more efficient at the same time. So this is shown here a bit. You can see here that Sam kind of compared those models, and you can see that the inference time can go down drastically. So you have the inference time while losing not that much of performance. So you can see here that I know you go down from, let's say, 24 to 22-ish in rouge score, which is not crazy much, but you more than half your inference time, which is great. This is even better for, so this was for XSUM, for the CNN Daily Mail data set was even better. So here you really go down from 1.4 to 0.9, while more or less keeping the same performance, which is great. All right, cool. Then the last slide on shortcomings and limitations is inductive bias that transformers have. So RNNs kind of are inherently sequence-to-sequence models because they're inductive bias that you kind of transform iteratively and recurrently the current inputs. So an RNN, if you think about all it does, the RNN, it kind of transforms its current memory to a future memory. And this is by default a recurrent mechanism. Transformers, on the other hand, they're not really a recurrent model by design. So normally what they're very good at is just processing big input length, but they're not super. It's not super natural for transformers to kind of sequentially upgrade your memory and autoregressively generate something new. So a big problem is, for example, that transform models they're not very good at generalizing to input length that they haven't seen in the data, because they kind of like just learn what output they should give for what length, but they don't really learn just the simple transformation you go from you need from I to I+1, whatever RNN does very well actually. I mean the remedy is that normally nowadays you just have all input length in your data, so it's not a big problem. But yeah, it's something which is not ideal. And there's this paper from Google as well, which is called Universal Transformers, where they try to tackle that, and they just said, all right, let's keep the transformer kind of like architecture on the time dimension, on the position dimension. So you just use sequence length, but let's make it recurrent on your depth. So you have a recurrent mechanism for how many transformer layers you're actually going to use. And this has been shown to generalize much better to input length that you haven't seen. So that's one nice approach to tackle that. Yeah, then there's one like other very fancy approach, which is called the fast transformers, where they use completely different kernels. Another self-attention kernel, which is not very recurrent kernel, but they create like their own kernel feature map, which behaves like an RNN essentially. And this it was just a super nice paper. The problem is that the kernel is so specific that it's not implemented in Torch, which means that it's very hard for us to kind of port the model to transformers, sadly. But a very nice paper. All right, yeah, I think that was it. So yeah, one last thing is I guess I want to show you is if you're interested in encoder-decoder models, we have some very nice blogs about it, some very in detail blogs which have some nice graphics and also all the math formulas. Which is the first one. The second one shows in detail how you can leverage pre-trained checkpoints for encoder-decoder models, which can save a lot of compute and give you very good results. And then I'd recommend to read two papers if you're interested. One is what I really like is a T5 paper by Colin Raphael, which does a super extensive analysis on all kind of encoder-decoder architectures and many different data sets, which is great. And they kind of started the mask pre-training objective for encoder-decoder models, which works super well. And the other one is the leveraging pre-trained checkpoints. I think I talked about already quite a lot. And then lastly, yeah, if you're interested in these kind of things, then yeah, I'd advise you to sign up to our newsletter, because we always talk about these things, current trends in our newsletter, and say what we integrate into transformers, and we're working on the moment. So I'm gonna kind of stay tuned with that. Then I hope you're gonna sign up for the newsletter. All right, cool. That's it. Yeah, if you have any questions, I think you can just post them, and I'll try to answer them.
Yes, or you can raise your hand and speak directly if you want. There is a hand here. Yeah, so let me try to, so the first one is Cristiano, yeah. Cristiano, can you, yeah.
Hi Andrea, hi Patrick, can you hear me?
Yes.
Yeah, perfect.
Okay, fine. So thank you so much, Patrick, and thank you for the presentation. I'm more into natural language understanding than a generation, so I really appreciate it. So I have been into natural language processing for 3 years now, but I'm a physicist. So recently, in my spare time, I went through quantum machine learning stuff. In particular, I was really curious about that it's possible to substitute some components, some layers with quantum ones, building somehow a hybrid quantum machine learning model. For instance, you can substitute some attention layers with quantum enhanced attention layers. And in particular, you can substitute some linear layer with variational quantum circuits. So the idea is to speed up things, but in reality, at the moment, this kind of substitution is slow, because you see classical quantum simulator are not so efficient at the moment, but we hope for quantum computing in the future. So my question is, in Hugging Face, are you looking at this kind of trends? So quantum natural language processing, or do you think they are at the moment too speculative?
I think, like, to be honest, we don't really look at anything which is related to quantum, I guess, machine learning. I mean, some people are very interested in, they read up on it on their free time, but it's nothing we really talk about seriously at the company. Because the problem is, I think it's still too much pure research for us. And
Yes.
what we really try to do is like research that works in production to kind of make it accessible for everybody. And I think quantum is not there yet, quantum machine learning. And to be honest, I really like, I don't know anything.
Yeah, you know, I was just curious about it, because really recently, let's say in the last 6 months, there are some, let's say, news about this kind of relation between a standard classical attention mechanism and its quantum version. And so I was curious about if you are looking at least into this kind of stuff, but probably they are too speculative. So thank you so much.
For sure, yeah.
All right, thank you, Cristiano. Okay, well, I guess you can reply to the questions in the question section.
Sure, yeah, I don't see any questions at the moment, but
well, one I can read them to you. He said,
okay.
What did you mean by the input dependent sequential length? I think this is referred
sure.
at the beginning, yes.
Sure, yeah. So the thing is, when you do sequence-to-sequence tasks, you don't know the output length a priori. That means that, for example, in translation, you're going to put in a sequence of, let's say, 10 words, but you don't know how long the output is going to be just by looking at the shapes. So it's kind of like an a priori unknown output length. On the other hand, if you just do in computer vision, you normally know the output length because your image has a fixed size, 32 times 32, for example. And then by your architecture of the neural network, you're gonna classify it down to I don't know, like depends on what you do, but let's say like 1,000 object classes. So you can like the output length, the output shape is deterministic. But the problem is in sequence to sequence, you have an a priori unknown input length. So the input length is well you have an a priori unknown output length. Sorry, so like the output length depends on actually the content of your input. So you need some kind of mechanism that treats the input and then realize at some point, right, like now I'm finished generating, and now my output is complete. That's why you have this end of sentence token kind of architecture in both sequence-to-sequence RNNs and sequence-to-sequence transformer models. I hope that answered the question.
Yes. And also a couple of people they're asking if you're willing to share the presentation, the slides.
For sure, yeah, for sure. I'd love to. Yeah. Should I just send them to you and then?
Yeah, sure. Send them to me, and we can put them, or if you can put them also in the comments of the Meetup page of your talk as well, sure. as you wish. Yeah. So I think I have some problems with the software because I continually see people raising their hands and then removing the hands. So I think if other people is just interested in asking question, they can write that into the question section. In the meantime, yes, we have another question from Elias. So the question was, do you know if there is some way to use a pre-trained model for generating non-correctly structured language? I'm merely referring to synthesized web search queries from documents, web pages. I tried with T5, but it was really not learning to generate non-syntactically correct text. Is it a limitation from being trained on prose?
So the question is whether you can generate what kind of text?
So I think not normal text, but kind of, you know, queries and something more like, yeah.
Yeah, actually, we have models for that. Actually, maybe I can find them right now. Even I can share my screen here. So yeah, we have models that actually here so that's our model hub. So I think we have some models on code, for example. Like we have a lot of models that can generate code, which I think is the question here more or less. So yeah, what you can do is normally you explore models, and I think we even have a tag which is called let's see. No, but then you should just be able to find something with code here. I think there's a T5 model on code. Yeah, for example, those are CodeBird. So that's a code model that was trained over here. Those were trained on code, so it kind of generates code. And I think we also have a T5 that generates code. So I'm just gonna go to T5, and then I'm just gonna look at all T5s. Then I think we have some code. Yeah, so those are actually those. So maybe if you so CBIS is called. Those are all T5 models which have been trained on code, so they actually can generate code, which is pretty cool. So I think here you can see an example. So yeah, well, it doesn't work on the inference API, but it was trained on code, so it can generate code. I don't know, I think we might even have a notebook on that. I think if you kind of search on Google, just Transformers notebook code T5, you'll find something. And yes, CBIS, I think, is the organization. They have a lot of T5 models on code. So I think you should check that out, and it should work.
All right.
Yeah.
Thank you. So Simone is asking another question. Hi, Patrick. What do you think about GPT-3 model? Do you think it can be a new approach to delete pre-train plus downstream task with one bigger, unique model that performs both?
Yeah, it's a good question. I mean, we are a bit afraid at Hugging Face that it's going to happen, because then our model hub doesn't make sense anymore. But yeah, I think one thing I kind of touched on in the presentation is that well, GPT-3 has to be updated constantly. It's super expensive. You can only ever use it in with the inference API of OpenAI. You're not going to be able to use this model even if it's open sourced, which is not going to happen. You're not going to be able to use it locally. So I think, well, GPT-3 does an amazing job at certain things like generating language, but you'll never use I think a GPT-3 for translation. If you are in production, just want to translate, let's say, from English to Russian or something, or English to Italian, then it doesn't make sense to use a GPT-3 model, which does everything. You're just going to use one model which was trained on that task, and it's going to be much better, more performant, I think, and more efficient at that task. So I don't think that GPT-3 is going to overtake all tasks, but I think it is better in some tests than all other models. And the idea that you can just use one model for everything is pretty cool, because it kind of allows OpenAI also just kind of have one model in memory, to have one model for everything, which is also a very good way to kind of have a product, right, for the user. To just kind of offer one model. That makes it very easy to run that. Yeah, I think it's impressive, but it's not going to take away all those other small models that work very well for very specific tasks. So yeah, I think sequence classification tasks, I wouldn't use GPT-3 for that. I mean, if you literally just want to classify a sentence into positive or negative, just use a BERT, because the GPT-3 in this case is you have to prime it with a lot of examples, and it's crazy expensive. So you run a crazy language model for a sequence classification task, which is 1/4 passing BERT. So I think it doesn't always make sense to use GV3, but yeah, if you do just text generation, then sure, it works crazy well.
Right. So if there are no other, okay, there is one question. Can T5 or Bart or sequence-to-sequence transformers in general be used for chatbots? If yes, how?
Yeah, they can. I mean, I think encoder-decoder models are the perfect models for chatbots. What I would recommend though is probably like T5 and Bart, they weren't really like trained, fine-tuned on chatting, but we have some. I think we have some specific models actually for chatting. Which is that already in here? No, but we have like BlenderBot is, for example, a model we have, which is very good at chatting. Okay, actually, what you don't see right now. So, oh, that's just T5. So yeah, like in short, encoder-decoder models work very well. Work very well for chatting, and we have some. Actually, this is a state-of-the-art model in chatting. It's called BlenderBot. So you should definitely check that out. It works super well in chatting. So yeah, I think it doesn't work on the inference API yet. You actually work on that. I think like the inference API is going to be up. Oh, maybe it works already. So BlenderBot is, I think, the best model for chatting at the moment. So it's from Facebook, from AI, and it's trained on chatting. It works very well. And then there's another which is called Dialog GPT. So those ones are also chatting models. Yeah. All right, yeah. So I would just check out kind of like the website for that. So this is Dialog GPT. It's also, oh, actually doesn't work here. But those models you can directly use them, and if you just follow what's written here in your code or BlenderBot.
Cool.
All right.
So this another question. I guess we can do like the last one or last two questions. Is there still any research/interest in using RNNs for text classification, or are transformers/BERT the preferred approach?
It's a good question. So, well, convolutional neural networks. I think there was a lot of research right on character-based kind of language modeling with convolutional neural networks, which was working very well. So there's kind of like now a revival of that because there's a convolutional BERT actually. It's called conv-BERT. So this one here, which also is just a kind of like a BERT model which works, which is based on convolution. So especially this one. Actually, if you're interested in that, you should check that out. This model, we added this a couple of days ago. So that's a model that kind of replaces the attention layer with a convolution, kind of like attention layer. But it's still like kind of has the architecture of a transform model. So it's just kind of it's a more efficient way of doing attention. So I think in general, yeah, I think attention kind of replaced convolutional networks and NLP for most tasks. I think it can be more efficient to use convolutional layers, but then it should also be an attention kind of paradigm, like it's done here. So if you're interested in that, I think I recommend kind of trying this out. conv-BERT, it's called. It's actually very new. I think we added this also last week. So and we don't even have a model card yet. So you can also just always like ask an issue or like ask a question on our forum for these kind of things. I'm always happy to answer.
Cool.
Yeah.
So we have time for just I think the last question.
Sure.
If someone wants to write one down. There are no more questions. Well, actually, if there are no more questions, I have one for you concerning models. Big models we discussed before. It's like we know that in NLG, generating high quality text, especially for long sequences, is very hard, right? So recently there was this model called ProfitNet, that was introducing this kind of strings of attention with the coding of, instead of 1 token per time step, and tokens per time step. So do you think that is the way, or one of the way to go to increase the quality of the text? And if so, when do you think, from a computational power point of view, we will reach the time where we can do, inference by decoding n times n tokens each time step?
So actually I added Profinet to the library, so I know the model very well. I like the model a lot. It's just not used. We don't really know, like no one uses it, and we actually tried notebooks and we don't really see people using it. And I think the problem with Profinet is that I think it's a very nice idea, and I like this n-gram kind of like training, that you not only predict the next token but the n next tokens. I think it makes a lot of sense to me, and the results on paper look good and the model works, but people don't really use it. Maybe like in half a year, people are going to realize that it's good and they're going to use it, but at the moment they don't use it. But I think it's one of many ideas which makes sense. So like I kind of talked about the task-specific pre-training of Pegasus, which is another idea which makes sense. And I think Profinet is just one other kind of like pre-training objective that makes sense. But yeah, like if you're interested, please try it out, because I'm always waiting for people to try it out, and I don't see any issues sadly on Profinet. But thanks for the question. It's a cool question.
Yeah. Cool.
And then lastly, maybe in general, this is like our kind of like newsletter website. If you're interested, huggingfacecurated.co. You can just put your email in. If you don't, you can also just see all the news here. So if you kind of want to be up to date with things like that we added BigBird, I think it's also in here. So with all these kind of things like new models, I think it's a very good way to stay up to date and new research. So
right. And also speaking of Hugging Face, Obeda is asking, any openings at Hugging Face? Smile. With a smile.
Yeah, we always look for new people. Yeah. So we normally hire over AngelList. So I think you can just go on AngelList Hugging Face. So AngelList Hugging Face, and then we always look for people. What we're especially looking for at the moment is TensorFlow. So we try to get our TensorFlow part as good as our PyTorch. So if you're good in TensorFlow, then this role is perfect. But yeah, like I mean, there are much more job postings now than there were a couple of months ago. So we're definitely looking for people. If you're interested in open source, I'm working on open source. I don't really work so much with sales or front end. So the stuff I'm working with is kind of like porting pre-trained models from big tech companies like Google and Facebook, and kind of interacting with the community. What I really like, then it's like these kind of jobs. So like the TensorFlow, like machine learning engineer or machine learning engineer and software engineer. So those roles are the open source roles. But yeah, we're definitely looking. Yeah.
Cool. Nice. So I still see a lot of hands popping up. So I think that's a bug of the software. So I think we are good to go. Thanks, Patrick, for the very nice, extremely interesting talk. As I said earlier, I just remind you about the next talk on the March the 16th on energy as well. So join us. And I think that's it. So again, thank you, Patrick, and thanks everybody for having joined us. And I leave the board to the organizer.
Great.
Thank you.
Bye, guys.
Bye.
Bye.
Ciao.
Ciao.